Next in Chapter 7 is recursion. So we're still doing combinatorics. This recursion refers to the kind of formulas that we can find for combinatorial problems. They're recursive formulas, and that means they refer to themselves, or the output refers to another output. Best to just see an example. Of course, it can't be an infinite loop, it has to terminate somewhere. But in this example, you have a sub n equal to 2 times a sub n minus 1 plus 5. So the sequence values, output values, a sub n, refer to sequence values a sub n minus 1, which is just the previous value. And that, of course, has to have an end. So we always tell you what n values it's valid for. In this case, n greater than 0. And then it has to have a start. a0 equals 1. So as in the recursion has to stop somewhere, and where it stops is at the starting value, a sub 0 equals 1. So here's a few examples if you haven't seen this recently to refresh. Put in n equals 0, a sub n equals 1, that's the given. Then after that, you use the recursion. For n equals 1, you do 2 times a sub 0 plus 5, which comes out to 7. For a sub 2, 2 times the 7 plus 5, so that'll be 14 plus 5 equals 19. And for a sub 3, 2 times a sub 2, which was 19, it gives you 38 plus 5 equals 43. Alright, so we'll see some examples where that kind of recursion is actually useful for, or it's the first thing you find when you study a combinatorial problem, counting something. But the idea now is to bring in the generating functions. We want to find a shortcut to a sub n so that you don't have to build the whole table. You don't have to keep on going back and recalculating all the way down to 0. So we'll try finding an ordinary generating function f of x, and then we'll use it in several different ways. There's options. After you find it, it gives you a bunch of choices to use it. Some shorter or longer, depending on how you like it. So there's the definition for an ordinary generating function. It has a sub n x to the n. So if you look at that and compare it to Maclaurin, a sub n there must be the same thing as the nth derivative at 0 divided by n factorial, all put together to make a sub n. Now here's the plan. You put both sides of the recursive equation into this sum. In other words, you fill them into this blank where it's got summation n equals 0 to infinity blank times x to the n. You fill in the left side and you fill in the right side. And of course, since they're equal, it's an equation, then you'll get a new equality. That n equals 0 there, that's going to be the starting value for the equation, whatever was given. So for our example, it will be n equals 1, because in our equation above, it said n strictly greater than 0, and the first counting number bigger than 0 is the 1. Alright, so that's like one of the crucial things. You have to decide what the starting value is, but it's a given. And then you take the sum from that starting value to infinity. You put the left-hand side of the equation in there, that was just a sub n. Then you write it again, you put the right-hand side of the equation in there, 2 times a sub n minus 1 plus 5. And then that's the setup. Now is just algebra. Lots and lots of algebra. So it's Calc 2 style algebra, but there's several tricks, and I'll illustrate a few of them in this example. First of all, looking ahead a tiny bit, the goal is to, let's look back up at the definition of an ordinary generating function. The goal is to pull out and algebraically separate pieces which we recognize. And one of them is the summation n equals 0 to infinity a sub n x to the n. Because then that's equal to f of x. So on the left-hand side, for instance, you have n equal 1 to infinity. I can start that at 0. If I started at 0, though, I better not change anything else about the function. So in the second line, on the left-hand side, I actually added 0 and subtracted 0. sorry, I added a sub 0 x to the 0 and subtracted a sub 0 x to the 0. That's the n equals 0 term. So the left-hand side has not changed. I should say, as we're going forward, sometimes we'll do the same thing to both sides of an equation. That's algebraically fine. Other times we'll do something to just one side of the equation, but if that's the case, it better either be multiplying by 1 or subtracting or adding 0. In this case, on the left-hand side, we've added or subtracted 0 because we put in the n equals 0 term, but then we immediately subtract it away. On the right-hand side, I did something different to start it at n equals 0. On the right-hand side, I shifted the index. That's also fine. It doesn't change the value at all. It used to go from n equal 1 to infinity, so I replaced all of the n's with n plus 1. Then I'll have x to the n plus 1. I'll have a sub n plus 1 minus 1, which is just a sub n. And underneath, I'll have n plus 1 equals 1, or n equals 0. Yep. So double check if you shift the index that when I plug in n equals 0 in the second line here on the right-hand side of the equation, I'll get 2 times a sub 0 plus 5 x to the 1. If I plug in n equals 1 in the previous right-hand side of the first line, same thing, 2 times a sub 0 plus 5 x to the 1. So I didn't make a mistake. All right, now third line, on the left-hand side, I see something that I recognize. It's f of x. It's the generating function, Maclaurin form power series for f of x. Another thing that I recognize is x to the 0, which is 1, and a sub 0, which was one of our givens. So that's 1 times 1 equals 1. On the right-hand side, I see some simple algebra that I can do. First of all, I can distribute x to the n plus 1 into those parentheses. And second, I can pull out an x. All right, I definitely did a couple of steps in one go here, so I would suggest taking what I wrote there on the third line and making sure that you agree it's the same as the right-hand side above it. In other words, just multiply some things back through. If you multiply that 2x back into the first summation, you get 2 times a sub n x to the n plus 1. That's what we would have had distributing the x to the n plus 1 above. And on the second summation, we have 5 inside. If we multiply, we have 5 times x to the n plus 1. Yep. So I just did distributing there and pulling things out. You can always pull things outside of a summation if they don't have n. They're just constants with respect to n. N is the only thing that changes as the sum is created. Yep, now there's some more things to recognize. N equals 0 to infinity, a sub n x to the n is f of x again. And that last summation is a known Maclaurin series, 5x over 1 minus x. Well, it's 5x times 1 over 1 minus x. And now there are no more infinities, no more summations. Everything is in terms of well-known functions and f of x. So the next thing to do is to solve for f of x. So I take the f of x on the right-hand side multiplied by 2x, and I collect like terms on the left-hand side. So I'll subtract that 2x times f of x. I also added the 1. There's a 1 on the left-hand side. I added it to both sides. So on the right, I'll now have 5x over 1 minus x plus 1. Then finally, I can divide everything by 1 minus 2x to get f of x all by itself. And now I have the generating function, 5x over 1 minus x, 1 minus 2x, plus 1 over 1 minus 2x. And that's a perfectly good answer if you're asked to find the generating function.